Good morning, and welcome to your science review with Mr. Blades. So, nobody's here yet, but let's go ahead and get started. Okay, so first problem. Let's have a box attached to a spring. Hi, first person, can you hear me? Yes or no? Let's say the spring is compressed 0.02 meters. It has a mass of 10 grams and it flies up into the air a total of 4 meters. I want to know what the K of the spring is and what is the final velocity just before the box falls all the way back down. And again, I'm looking for any indication that you guys can hear what I'm saying. Can you hear me, yes or no? Just somebody type yes. All right, well, whatever. Okay, so when we're doing a problem like this, we need to figure out what we know the most about, okay? So we know we're going to have to find the K. We know we're going to have to find the velocity. So already you should be thinking about our potential energy equations for a spring and our kinetic energy equation with a velocity in it. But we don't know K and we don't know the amount of energy, and we don't know V and we don't know the amount of energy. But we do know the height, the mass, and the acceleration due to gravity. So we're going to go ahead and start with our potential energy, mgh, or Mr. Blades, why did you change that to 0.01? Why did I do that? Anybody know? Okay, good. And why did I change this from 10 grams to 0.01? Anybody? Well, either way, it's because our original mass was in grams and we have to change it into kilograms, right? So 0.01 times 9.8 times 4 equals 0.392 joules. Somebody please check my math for me. Yep, there we go. That's perfect. Okay, so that is the total amount of energy in the system. And we know that because way up here at 4 meters above the ground, it has slowed to a stop because it's about to fall back down, and there's no spring up here. So there's no spring, there's no kinetic energy. The only kind of energy we have is potential energy. There we go. I can see your responses now. All right, so we know that this right here is our total amount of energy for the entire system. And now we can use that. To move us through the rest of the problem. Okay. So before, when we were talking about the potential energy of the spring, our equation PES equals 1/2 kx squared. We didn't know the potential energy, and we didn't know the K. That was two unknowns. But now we know the potential energy. Okay. So we have 0.392 2 equals 1/2, whatever k is, times 0.02 squared. And if we divide both sides by 1/2 of 0.02 squared, that gives us a k of, you can't see it, 0.392 divided by 0.5, enter, divided by 0.02, enter, divided by 0.02 again, enter. So we end up with a k of 1,960 newtons per meter. And again, because we have our newtons in here, we must have our mass in kilograms. Okay. Next, I got a little space under here. Next, kinetic energy, 1/2 mv squared. And again, before we didn't know v and we didn't know ke, but now we know the ke, so we can have 0.392 equals 1/2 our mass 0.01 multiplied by whatever our v is squared. Divide both sides by 0.005, which is just 1/2 of 0.01. Gives us 78.4. And if we square root 78.4, we end up with a velocity of 8.85 meters per second. And just for the record, right there, x is right there. And for the record, x is compression of the spring. Okay. Is there degree questions? Fair. I will do one. But before we leave this problem, this 8.85, if we notice, there is a mass in the original calculation of 0.392 and a mass down here. So what that actually means is, mass would cancel out on both sides. So this 0.1 would cancel out this 0.01 up here. And so as a result, any object falling from this height would attain that velocity regardless of mass. Okay, let's move on. Okay, if you don't know how to convert grams into kilograms, that is something we've covered in literally every unit since August, so that's on you. Okay, next, box, mass of 2, velocity 1 meter per second, experiences a force of 2 newtons, and after a certain amount of distance, it is now the same box but traveling 4 meters per second. Okay, that's supposed to be the letter D. I don't know if that's any good. All right. Okay, I want to know, how far does it travel with this force of 2 newtons to get it from 1 meter per second to 4 meters per second? And if the time it takes is, let's say, 3 seconds, how much power is spent doing that? Okay, so the reason I bring this up is because there's an important point that I feel like gets missed. Work, which is force multiplied by distance, is the same as the change in energy in the system. In order to change energy in a system, you have to apply work to it. You have to add energy to the system by doing work. Okay, and so what we're going to do is we're going to find out how much energy has been added from here, between here and here. Okay, so we have a certain amount of energy here. We can see that, and that would be true even if the velocity were 0. It would have a certain amount of energy, and over here it has a certain amount of energy. We can calculate both those energies, and as a result, we can see how much work is done. And then there we move on from there. So let's figure it out. Our change in energy is just our energy final minus our energy initial, which is, not news. So our energy at the final is all kinetic because it's all moving along one plane, so its potential energy isn't changing any. So we have 1/2 mass times the velocity 2 squared minus 1/2 m velocity 1 squared. And we can just go ahead and put that all in. So 1/2 times, okay, let's go ahead and make that explicit, 2 kilograms. 2 times 4 squared minus 1/2 2 times 1 squared. And we end up with, we can factor out this 1/2 and this 2, and 1/2 and 2 equals 1. So we just end up with 4 squared minus 1 squared, or 16 minus 1, or 15 joules of energy added to the system. And like we said, that's just equal to our work. And even though I would like you to do this one last, we can go ahead and do it pretty quick, because like we should remember, power is just work divided by time. And in this case, it's 15 joules per 3 seconds, or 5 watts of power. Boom, done. Next, let's figure out our distance. And again, we've already said that work is equal to our force multiplied by our distance, and we have our work already. So work equals 15 joules, and we know our force over that period of time. So 2 newtons times whatever our distance is, divide both sides by 2. And we have our distance of 15 over 2 meters, which would be perfectly acceptable, or 7.5 meters. Both those pretty straightforward. Okay, cool. Now, I like to explain where things come from, so let's go ahead and actually work that little bit out and see the origin of an equation that we use a lot earlier in the year, and I actually didn't realize we were still using. So our work is equal to our force multiplied by our distance. Force is equal to mass times acceleration. So we can go ahead and plug that in. So our work is equal to mass times our acceleration multiplied by our distance. And we already said in the last bit that it was equal to 1/2 times the mass v final squared minus 1/2 times the mass v initial squared. Okay, and again, we can divide this whole side. Well, first things first, we can get rid of all these masses, right? They all cancel out. And we can multiply both sides by 2 to get rid of these halves. So there we go. We end up with 2AD equals VF squared minus VI squared. And if we add VI squared to both sides, we end up with an equation we use a lot in projectile motion, that VF squared equals VI squared plus 2AD. Okay, that equation should look very familiar to you guys, and it's just the work and energy equations put together. So we've been using those the whole time. Okay, I'm going to do an angle problem for the K kids. Anybody? Okay, fair enough. You can get rid of stuff if it appears on both sides of the equation. I like to simplify things so that I do as little arithmetic as possible. And as a result, I have the lowest number of opportunities to make a mistake. And when you get into higher order mathematics, you'll see a lot of shuffling the symbols around long before you put any numbers in, actually. Okay, so I'm going to do a problem with angles for the K kids, and anybody else is welcome to think of a question to ask me in the meantime. And by the time I'm done with it, I will do whatever the best question is. And if not, then I'll wrap it up. Is this test easier than past ones? Well, it kind of depends on what you mean by easy. I'm not really a great person to ask about stuff like that. I think they've all been easy. This one does have less trig on it, though. Okay, so here we go. Yeah. Da, 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 da. Okay, so let's say 30 degrees for that. And we have a block, mass of 3 kilograms. We have a K of 1,000 newtons per meter. Okay, so the spring is compressed a certain amount of distance and it's released. It allows the block to slide up, and then it slides up this ramp at 30 degrees. It will travel. Oh, okay, we don't actually need to know that. How far up, or how far will it travel in this direction up the guy? And what is its maximum? Oh, okay, that's why. Okay, so if it travels 15 meters up the ramp, what was the velocity that it hit the ramp at, and what is the displacement of the spring? There we go. I think we have enough there. Okay. And again, it all starts with energy. We have to know how much energy we have, okay? And we don't know the total amount of energy yet. We don't know the velocity. We don't know the x. So we can't calculate the kinetic energy, and we can't calculate the potential energy that was stored in the spring. So, of course, the only thing that we end up with being able to calculate is our gravitational potential energy again. And we remember from 100 times of doing this that this is our potential energy. And of course, our potential energy right here, this is our height, just how high up above the ground it gets. Okay, so our height here is actually 15 times the sine of 30 degrees, because this is the opposite side of this angle. So we can rewrite this equation as mass 3 kilograms multiplied by 9.8 meters per second squared multiplied by 15 times the sine of 30. So let's go ahead and calculate that out. Don't forget to be in degree mode. Okay, so clear. 15 times the sine of 30 degrees. And the sine of 30 degrees is 1/2. So it's 7.5 equals times 3 equals times 9.8 equals. Okay, so our potential energy that was stored by traveling up the ramp was 220.5 joules of energy. Okay, that's not a 5, that is a J, even though it looks a lot like my 5. And now, again, we can solve for all the same stuff. So our potential energy that was stored in the spring, again, potential energy that was up here must have come from the spring. So these two things have to be equal. So 220.5 equals 1/2 kx squared. But this time we know the k, but not the x. So we're going to divide both sides by 1/2 of k to get rid of both of those things, and divide both sides by 1/2 of k. And in this case, k is 1,000. So x squared equals 220.5 divided by 500. Or 0.441 1. And if we square root both sides, we end up with x is equal to 0.664 meters. Boom, there we go. And again, our kinetic energy must be the same too. So 220.5 equals 1/2 times 3 v squared. Divide both sides by 1/2 of 3. 0.5 divided by 1.5. So our v squared equals 147. If we square root both sides, v equals 12.12 meters per second. Okay, there you go. Okay, now some important things to remember are whatever our object is that it's working on. Oh, fair. I can address that a little bit. Okay. Okay. I'll do one. I'll do one of those. So whatever is happening, so our person on our boat or a block on a spring or whatever, that is our system. And you can imagine a circle around it or a barrier around it. Nothing gets in and nothing gets out. Whatever energy is inside here is all there is. Okay? And the simplest way to solve most of these problems is to find a place somewhere on the roller coaster where no other energy can exist. Okay, so like in this one, it'd be any of these spots at the bottom. There, only kinetic energy would be allowed because it's even with the ground, so no potential energy. Or way up here at the very top, where it would be nothing but potential energy and no kinetic. So when we're solving for these things, that's going to be the place you start, is find out exactly how much energy is in the system. And the way to do that is to find a spot somewhere in the system that only one kind of energy ever could be there, and then solve for what it is there. Normally, we will have given you enough to be there. Also, if a thing weighs 3 newtons, it requires a force of 3 newtons to lift it. Okay, like just assume that unless we give you some other idea. Okay, so how to solve for dissipated energy. This one's simple, so I'm going to just show you quick. Okay, so let's say, and let's hope this turns out right because I'm making this problem up. So at the bottom here, it's 1 meter per second is the velocity. Up here, we have a, ouch, okay. Okay, so down here, velocity equals 1 meter per second. And up here, we have a box with a mass of 2 kilograms, but we'll find out that doesn't actually matter. And let's say we are 10 meters off the ground. 10 meters off the ground. How much energy was dissipated? Okay. Question. Okay. So just like I said, we're going to start by figuring out some place in the system where no other kind of energy can exist. And right now it's at the very top, and just like normally is the case, I have given you enough information to solve up there. So our potential energy based on the position of that block at the very top of our hill is equal to mass times the acceleration due to gravity times height, or 2 times 9.8 times 10. Or let's see if I'm right, 196 joules of energy. 2 times 9.8. Yep. Okay, so 196 joules of energy. Now, down here, let's go ahead and say that there is friction. I just haven't told you what it is, and frankly, it doesn't actually matter. We could figure out the coefficient of friction, but that's beyond our pay grade for this. But anyway, now down here, we also know enough to calculate our energy down here as well, and we would use our kinetic energy, 1/2 mv squared. And in that case, it'd be 1/2 times 2 times 1 squared, or 2 times 1/2, 1, or equal to 1 joule. Now, I hope it becomes obvious at this point to find out exactly how much of the energy has dissipated. We started off with 196 joules, and now we're down to only 1. Our change in energy, or our energy that must have been dissipated because it didn't get turned into motion, is our 196 minus 1, or 195 joules of it just went into heating up the slide. So anyway, done a work, a power, an energy, a dissipated, one with angles, and answer some questions. So I feel like you guys have gotten all the use out of me that you'll get for today. So I hope this was helpful, and good luck tomorrow, and I'll see you in class.